You also recording?
I'm sorry, Tushar?
Oh, sorry, I was just asking if you're also recording. I guess. Perfect, thank you. And I can see Alexei is also here. So yes, perfect timing. We can get started. Hey, Alexei.
Yeah, sure. Thank you.
Hello, everyone.
Hello. Hey, Alex. Just in case, so this morning my internet is not that stable. So just if some reason I'm disappeared, we posted alternative link in the chat box, just in case if I'm dead for a couple of seconds, and we can use the alternative link. So okay. Sorry about that. And so today, thank you everyone for coming to the talk. And we are really happy and honored to invite Xinyu Chen to come to give us a talk on his impressive work. So let me give Xinyu a really brief introduction. Xinyu is currently a PhD candidate at the School of Computing, National University of Singapore. And he has been working on FPGA-based hardware acceleration for emerging application domains such as graph processing and database system. So he's currently working with Professor Bingsheng, Professor Wei-Fai, and Professor Deming Chen, and also my awesome collaborator, Dr. Yao Chen. And we are really glad to have you here, and it's all yours.
Thank you very much. Okay, so now maybe I can start. Okay, it's also my great pleasure to have this talk here, and thanks this opportunity also. So today I'm going to talk about our work about HLS-based graph processing or FPGAs. So just as introduced before, this is a joint work with Hongshi, Yao Chen, and Prof. Bingsheng, Weng-Fai, and Prof. Deming Chen. So firstly, I need to give you some background of graphs. So why graphs are so popular and important? This is because graphs are very important data structures that can represent the relationships of different entities of diverse applications. For example, social networks, web graphs, and biological networks. And as we all know, we are in the big data age. The data is actually exploded. For example, the Facebook graph can contain more than 1 trillion edges, and a World Wide Web graph can contain 200 billion edges, and the human brain can contain up to 1 quadrillion edges. So with such large-scale data size, we want to still make graph analytics practical and usable. So there we actually need a very high-performance graph processing to process them as fast as possible, and also we want to the processing as energy efficient as possible. So to achieve very high performance graph processing, the first problem we need to dig into is that we need to consider which architecture for graph processing. The first architecture we consider should be CPUs, because it's very general and also it's everywhere. You can find it in any server, right? However, for CPUs, the problem is that the performance is limited by the end of Moore's law and then the scaling. Let's see the first figure. Basically, it shows the Moore's law scaling with the real transistor density according to the time. As you can see from this figure, the gap is getting larger and larger, which indicates the end of Moore's law. In the second figure, we can see, according to more advanced technology, as you can see from this red line, the power is not constant anymore. Actually, it is significantly increased. That indicates the end or Dana scaling, which means we will suffer from cooling problem of our chips. So all this indicate the performance of CPU or successive CPUs are not going to be improved significantly. But once there are challenges, there are solutions. So just as advised by David Patterson and Hannes, domain-specific architectures, which is DSA, can be the future for certain applications. This is because the DSA can usually achieve a better performance because they can be more closely tailored to the needs of the application, right? So we seek, DSA solutions for graph processing. However, there are, several DSAs like GPUs, ASICs, and FPGAs. So why we finally choose FPGAs for graph processing? Let's first look at GPUs. Definitely, GPU is very powerful, and also it's very flexible because you can change the execution binary in a very fast manner. So the flexibility is very good. However, the problem is that it suffers from branch divergence because graph processing is typically irregular. However, the GPUs is well known for batch processing. So there is a mismatch between architecture and workload. And also another increasingly important issue of GPUs is that they are power hungry. So then let's see ASICs. Definitely ASICs deliver the best performance. This is very easy to understand. However, the problem is also very significant. It has poor flexibility, and also the cost is very high. You need to you also need a very long development period, and the time to market is too long to accept. Instead, FPGAs achieve a very good balance here. So firstly, you can also enjoy the magic of hardware customization as ASICs. So you can have specialized memory optimizations for your graph processing. Yeah. Secondly, it also has reconfigurability. We don't need to. We can actually change the bit stream of the FPGA to adapt to evolving graph processing applications. Lastly, recently there are high-level synthesize tools for HLS, which can translate high-level languages like C or C++ to low-level HDR languages, such that it can deliver a very good programmability. And also, I believe with high-level languages is pretty good for large-scale systems, not only the programmability, but also the maintenance and the usability. So, and also we can see from some existing studies, FPGAs already deliver, a very significant speed up in some certain applications in data centers. So considering all about this, we try to explore FPGA-based graph processing, especially with the HLS. So basically, this is our, research motivation. So then I will introduce the journey of graph processing on FPGAs. So firstly, we look at the challenges of graph processing accelerators with the HLS especially. So we find the challenge is runtime data dependency, and we solve that by on-the-fly data routing. And in the next stage, we try to jump out the box to look the problem in a higher level. So we want to see whether there are system-level support for graph processing or FPGAs, to really make FPGA-based graph processing take off. Unfortunately, we didn't find that, so we actually developed one, which is SunderGP. So in the next, I will first introduce the challenge of graph processing with HLS. I will need to first introduce the main computation of graph processing, which is edge traverse. Let's say in this example graph, basically for an edge traverse, the source vertices will propagate its property to its neighbors. So here in this example, the vertex 1 will propagate its properties to vertex 2 and vertex 7. Vertex 2 and 7 are both neighbors of vertex 1 right here. So, there is a vertex property array which, stores all the properties of different vertices. So in terms of execution, we firstly need to, read the vertex 1's property, and then we do an accumulation with the vertex 2's property. Then we try to write it back to vertex 2's property. And we do the same thing for vertex 7's property. So as you can see from this execution, there are some features of graph processing. Firstly, we have random memory accesses because the neighbors of one vertex can be very far away from each other. So the access to this vertex property array can be truly random. In this example, they are very close because this graph is very small. Once they are very big, these numbers can be very far away from each other. Then access to this array can be very random, right? Secondly, it has very high communication to computation ratio. Let's say in this example, we actually read and write several data, but we only do one computation, like accumulation, which is. So given these characteristics of graph processing, there are some common techniques of graph processing accelerators. The first one is data buffering with BRAMs, because as mentioned before, the access to vertex property array is random. But if we buffer this property array into BRAM, then we can enjoy the feature of BRAMs that is low latency and high support for random access, right? Of course, we need to do graph partitioning on the software side. Another technique is multiple processing elements, such that we can process multiple edges per cycle to increase the overall throughput. Combine them together, each PE process a partial of data. Let's say the P0 process destination vertex from 0 to 3. Because why we want them processed independently? Because we want to maximize the throughput of each PE, right? So in this case, actually, we need a logic to dispatch these edges to different PEs, because each PE only processes a partial of data. So in this example, the first edge will go to the P0, and the second edge will go to the P1, because its destination is located in P1, right? So actually here we need a data shuffling logic, to dispatch this data to different PEs at runtime. Actually, this in this example, the connection is static because it demonstrates this example graph. But in reality, the edges can be arbitrary, right? So we need a logic to assign this data to arbitrary PEs at runtime according to their destination vertex. So here we firstly introduced the definition of this shuffling. Basically, it's widely used for irregular applications. Let's say the data tuples generated from one stage is going to be dispatched to the upper stage according to their value. Let's say in this here we want to dispatch these tuples according to that destination. These connections are not static because the data can have any value. So it's a runtime data dispatching. So which PE to go is determined by their value. So compiler cannot know this connection at runtime. At compile time. So it's like there is a fully connected network here. So what's the challenge of doing this with HLS? So firstly, there is no fine-grained control logic for HLS. Because if you are using RTL, you can use some network on chips for solving this problem, right? You can routing the corresponding data to your destination. However, for HLS, it's not possible. HLS is using the data flow model. Secondly, there is also no vendor-specific extension for this data shuffling, which has been argued by another work, actually. And lastly, it's very important, HLS only conducts static analysis at compile time. So this logic actually requires some runtime information. So in this case, HLS fails to extract parallelism in such kind of functions. We also survey existing works to find some potential solutions. The first is the naive pooling method. Basic idea is that each PE checks the tuples one by one to see whether it needs to process current tuple. Otherwise, it just skip it. However, the problem is that we waste some cycles in checking the tuples that doesn't need to be processed. So in this case, we actually need 8 cycles for dispatching a set of 8 tuples, which have very low, parallelism. For the second potential solution is convergency kernel. The basic idea is that, each PE tries to write only the tuples they need to process into a local buffer, and then they process these tuples one by one by reading this buffer. However, the problem is that, write the tuples in parallel to this buffer is introduces runtime dependency, because the write index of one tuple is determined by whether other tuples need to be right? So actually, the runtime dependency is still there and not solved anyway.
So Xinyu, I had a question.
Okay.
So I actually have 2 questions. So the first is, suppose you were running this on an ASIC and you actually had a separate shuffle network. Do you think that would have made this problem go away, or would it have made this more efficient?
Okay. So firstly, if you are running this logic on ASIC, maybe you won't choose HLS as a programming language. You can use some network on chips to solve this problem. Basically, it's try to routing the data according to their value to their destinations. It's
exactly. That's what I was trying to ask. Like, if there's a very specialized network on chip, this would have been easier. So the problem here is because nothing like that exists on the FPGA, correct?
Yeah, right. It's because of HLS, so you don't have fine-grained control logic and like ITR. Yeah. So
thanks. And another follow-on thing was maybe a little bit on talking about. So now in the Xilinx Versal chips, right? They have the AI core. So from what I understand, or at least what I've read in the documentation, they have some kind of a shuffle interconnect inside to kind of shuffle things between the vector units. So do you think something like this would, again, show much better performance there, or do you still think this will be a challenge? Maybe I'm trying to understand how much of it is this a challenge because of HLS, how much of it is a challenge because of just the way the FPGA is in terms of its structure.
For our work, actually, this problem is mainly because of HLS. So, of course, for Xilinx, the latest device, you already have hardcore AI engine. If you want to, dispatch the data efficiently, it's better to have some, hardcore data routing logic in there, right? I guess that is the case. But in our, platform, we are using, just the FPGA with no hardcore, so we need to design, the logic we need by ourselves. Yeah.
Thank you.
For example, current HBM-enabled FPGA platform, they also have some crossbars that can let you access different channels and hardcore crossbars that can be more efficient. But our current work is trying to solve that if we are using HLS to do this kind of logic, can be very inefficient if we are using the traditional method, and also it will downgrade the performance of graph processing or FPGAs. Yeah.
Got it. Okay. Thank you.
So basically, this runtime dependency is very costly. The RI can be very high, which can be up to 300 cycles. That means this method is even worse than pooling method. So we're thinking this pooling method actually introduces bubbles, and the convergence kernel doesn't solve the problem. So we are thinking, what if we know the positions and the number of wanted the tuples to be processed in advance, such that each PE can directly access the wanted tuples, right? And also the cycles needed can be equivalent to number of wanted tuples because we do not waste cycles in checking unwanted tuples. The problem is how to know the positions and the number of wanted tuples. So we propose a decoder-based solution. The main idea is that for example, for a set of 8 tuples, because each tuple only has 2 statuses for a PE, which is to process or not to process. So for 8 tuples, we have 256 possibilities. So we can enumerate them into a table. Then we can look up them during the execution. So here I will show an example for a set of 8 tuples on P0 as an example. Let's say we have 8 tuples with their index here, and we firstly calculate their destination PEs in parallel. And then we try to compare their destination PE with current PE idea to see which tuple need to be processed by current PE. Let's see the tuples in index 6 and index 2, they are with destination PE 0, right? So current PE is 0, so they are matched. Then we correspondingly mark them as tuples to be processed. Others, we just mark them as 0. Then with this mask code, we can actually decode out their, the numbers of tuples need to be processed and also their positions, because this mask code is one possibility in the table, right? And based on this information, then we can directly access the wanted tuples with a for loop. Basically, the trip counter we can set to number of tuples, and in each iteration we just fetch the corresponding position, such that we don't need to check other positions and saving a lot of cycles. So with proposed method, we actually do not waste cycles, and also the runtime determinacy is solved, and all the modules are pipelined. So then we evaluate the efficiency of our data shuffling. So we firstly compute the throughput of our data shuffle. So as you can see from this figure, it's very close to theoretical throughput. That means, let's say your memory interface can read 8 tuples per cycle. Our data shuffling can actually dispatch 8 tuples per cycle if there is no congestion, if the data is not skewed, I mean. And we also compare with other solutions, which I mentioned before. As you can see, our method is much faster. When the tuple size is very small, then our memory interface can read multiple data per cycle. In this case, the throughput is more critical, so we can deliver a higher throughput here. The worst case is that the tuple is very big. One cycle you can only read one tuple, then there is no difference for 3 methods, right? But actually, this is usually the case for graph processing because the edge is only 2 integers, so memory interface can read multiple data per cycle, not only one. This is the way to fully utilize the memory bandwidth. Okay, so now we actually tackle the challenge of doing graph accelerator with HLS compared to the logic with the RTL. So then we're trying to see whether there are some system level support for graph processing or FPGAs. So like we want to somehow like make this ecosystem better. So we are thinking in the high level we have graph applications, maybe from data scientists or from software developers, right? In the low level, we have hardware, which is CPU FPGA heterogeneous platforms, right? So we are thinking, what should we have in between to bridge these 2 levels? So we are thinking, do we only need the graph accelerator design methods? We don't think so, because with only design methods, the developers still need to coding from scratch and doing optimizations by themselves, and also this is a very time-consuming process, and also it requires a a lot of hardware expertise. So we think there is a need of system level support, such that even software developers or data scientists can enjoy the speed up of FPGA-based graph processing. So we firstly need to look at whether there are some existing works can achieve that. So we look at how systematic are existing studies. So in this table, we survey existing FPGA-based graph processing works in terms of frameworks and library and also accelerator architecture. We survey whether they have APIs and what are the languages they are using and whether they have automation and how do they conduct evaluation and whether they are publicly available. So firstly, we can find no of them using APIs, and most of them are using hardware description language, which is not friendly for software developers, right? And very few of them use automation. That means developers still need to tune in the pipeline and tuning their design. Even worse, for evaluation, most of them are using simulation and are not publicly available. This actually forbids some people using their work. And for applications, they usually conduct a few applications for evaluation. So in summary, we think existing studies have poor programmability due to HLS-based programming and no user-friendly APIs. And also they require manual performance tuning like pipeline composing, design space exploration. Those are very time-consuming and not easy to do actually. And also they have poor usability because they are not open sourced and they are not ready-to-run systems. So knowing there are no such kind of systems, we decided to design a high-performance system for graph processing or FPGAs. We think that is important, but actually achieving high performance as well as good programmability is not easy. So there are several challenges. Firstly, we need to support various graph processing algorithms because there are too many algorithms like BFS, SSP, PageRank, WCC, and so on and so forth. So to solve this problem, we actually design an efficient architectural template with the adoption of the JS model, which can adopt different algorithms. Secondly, we need to enable programming without hardware expertise because many users will assume they are not familiar with hardware. So to solve this, we try to expose only high-level APIs to developers. And importantly, our system takes the rest to generate a synthesizable code for developers. Lastly is actually the most important part. We need to unleash full potentials of these state-of-the-art FPGAs because performance is the key. So that's the reason the user want to use FPGA-based graph processing. And current state-of-the-art FPGAs are very complex. They have multiple SLRs and multiple memory channels. So we actually propose some heuristics to scale our architectural template to multiple SLR FPGAs. And also we schedule the graph data to utilize the generated accelerator correspondingly. So combine all these solutions, we propose StandardGP. So in the next, I will firstly give an overview of StandardGP. So basically, it has three core components. The first one is Accelerator Template. Basically, it provides a general architecture for different graph processing algorithms. And also, it has accelerator generation. Basically, it generates the synthesizable code with the input from users as well as the accelerator template. And lastly, on the host side, SunGP has graph partitioning and scheduling method that can pre-process the graph data and schedule them to coordinate with the generated accelerator. So in terms of workflow, the developers just need to write the functions or scatter, gather, and apply, which are actually functions for customized processing logic or their graph processing accelerator. And then user need to assign the underlying hardware platform, because SunGP relies on some specs or the platform to do some space exploration. Finally, the SunGP can generate the accelerator by itself. The developers just need to assign the graph data set they want to process on the host side, and our library can do graph partitioning and scheduling, and finally, the whole system can run in a push-button manner. Okay, in the next, I will introduce the accelerator template, and then the accelerator generation, and finally the graph partition and scheduling. So, accelerator template is very important. It guarantees the high performance of different algorithms. Basically, it's like we have some design constraints there. So, the users write some functions in this space, we can promise a good performance. So actually, it adopts the gas model. Let me introduce the gas model in a very brief manner. So basically, gas model is still about traversing the edge. Basically, it has 3 stages. In the scatter stage, for an edge, let's see this edge from vertex 1 to vertex 2. For this edge, an update tuple is generated with the format of destination and value. The value is calculated by the source vertexes property and edge property. Let's say in this example, I just use x to stand this value. So for these 2 edges, we will generate 2 update tuples here. In the next stage, basically, each vertex will accumulate the values to destination. It will accumulate the values to destination vertices. Like in this case, the system will accumulate the the updates from vertex 1 to vertex 2's property, and then write it back. The final stage is the apply. Basically, we update all the vertices for the next iteration. So those are 3 functions that can be tailored to different graph applications. So SunGP exposes 3 functions to developers to customize the hardware logic for their application. And also the execution flow of hardware of this gas model FPGA is like this. So we also have vertex buffering with RAMs to avoid random memory accesses to the vertex property array. And also we have multiple PE with the previous proposed shuffle to process multiple edges per cycle. With shuffle, actually we can avoid data reordering because it solves the runtime data latency at runtime. And also it can enlarge the graph size processed on chip because we can let different PEs process different data. Yeah, this is the diagram of this shuffling enabled processing, pretty similar with the previous one. And also we pipeline the scatter and gather inside FPGA, inside of a BSP manner. Previous study may process the scatter at first and then write the results back, and then process the then conduct the gather stage. So if we pipeline them inside FPGA, we can reduce memory accesses to the global memory, and we can better explore the pipeline parallelism. However, this execution introduces one side effect because we only buffer the destination vertices, we do not buffer the source vertices. So we need to access those vertices from the global memory. Because we are processing the CSR format, those vertices are already in ascending order. However, even though the access will still issue one request to memory, as there is no transparent caches in FPGA. This is also a good point of FPGA because we exactly know what is our memory access pattern, so we can have some specialized, customized memory optimizations for our memory accesses. So correspondingly, we deploy 4 memory optimizations. The first one is caching, because one vertex may have many neighbors. Maybe the vertex may be accessed for multiple times, so we can cache them for data reuse. Secondly, we have coalescing, because those vertices accessing those vertices from different scatter PEs cannot be far away from each other because it's already in ascending order, right? So we can coalesce them together to reduce the number of memory requests to the global memory. We also have perfetting, because the request address is monotonically increased, so we can perfect the vertices for future use. Lastly, we also have execute and access decoupling, because graph is too regular to have a very stable throughput. So the throughput is sometimes just fluctuate. So if we have execute and access,
so another question to clarify. So these the template is independent of the number of PEs, right? So you can instantiate this for any number of PEs. Of course, the total number of PEs will depend on how many fit on the FPGA, but the template itself is completely scalable, correct?
Yeah, it's scalable. In the next, I will talk about how we scale our template to multiple SR FPGAs. Because currently it's just an efficient, data path, an efficient pipeline.
And the other question, maybe you can decide whether you want to answer this now or towards the end, but this template, as you said, is quite general, right? It has a notion of scatter, gather, and data coalescing.
Yeah.
So, which is great for graphs, but I presume this will also be general enough for other maybe HPC applications, or even if I'm just doing DNNs, if I'm just looking at sparse DNNs like that, this might also work there, correct? Or is there something that's very specific to graphs?
Actually, guess model is pretty specific to graph processing. Yeah. So actually, this is a very open problem, I think. Yeah. Actually, to be honest, even for graph processing, the guess model also has some limitations. It's not that general enough, because graph processing is very diverse. Guess model sometimes cannot express some algorithms.
I see.
So for other HPC applications, it's very hard to see.
Yeah, so maybe I think going to very HPC might be hard, but making it even narrower. So for example, when the thing I liked with the whole approach is when we've been thinking about, and as you know, right, so since I come from a on-chip network background, and that's partly why I was asking you about shuffle networks and so on. So the way we've been thinking of this more for ASICs is that, but that can even apply for FPGAs, is a bunch of processing elements, some SRAMs, and then some primitives for doing scatter of data from VRAMs to the PEs and then gather of the outputs. And if it's sparse, then it's really scatter and gather. I mean, if it's dense, it's more it's very stylized. But if it's sparse, it's literally scatter gather, kind of similar primitives as GPUs. And of course, in our case, we also have a very specialized shuffle network to implement the scatter operation. But that's why I was curious, do you think this is something that will also work for just DNN accelerators?
Xinyu, okay. So, sorry for cutting in. I think the answer to this question is the shuffling part in this design. It's actually flexible enough to deal with any other sparsity related topics like the GNN or even DNNs, the sparse DNNs. But the other part, the guess model, is specific for the
graph processing.
And well, I should see it's a twofold this thing. If we focus on the graph processing, then we have to provide a specific model for it.
Yeah, but for this shuffling, if maybe you are using RTL, I would say maybe you have a better choice to solve the similar problem. But if you choose HLS, definitely it's a very good choice. I mean, the solution. Yeah. Okay. Maybe let me continue. Okay,
Yeah,
so
thanks. Continue. Yeah.
okay. So far I just talk about the like a primitive. We have a template there. It's highly optimized to guarantee high performance, essentially, right? So in the next, I will introduce how we scale this template to fully utilize the resource of the FPGAs. Basically, current FPGAs are very complex. Like they have multiple SLRs and multiple memory channels located in different SLRs. However, there are also some challenges like crossing SLR will result in very bad timing, right? Because the delay is longer. So we actually have principles that we do not let kernels cross SLRs to ensure a very good timing. And also we try to fully utilize the memory bandwidth of the platform because, as we mentioned before, graph processing is has very high communication to computation ratio. It's very memory bandwidth bounded. So if we want to achieve a very good performance, we must fully utilize memory bandwidth, right? So following these two principles, we have developed automated steps. Firstly, we calculate the required number of kernels according to the memory bandwidth of the platform, and then we try to fit these kernels into multiple SLRs. So I will introduce steps one by one. So firstly, we calculate the kernels. The main idea is that we know how much data we can read from the memory interface per cycle, right? We also know the RI of 1PE, so we know how much data 1PE can process per cycle. Then we just try to balance this pipeline to calculate the required number of PEs such that we know the required number of kernels, right? Then we scale this number to the number of memory channels, so we can have a total number of kernels to fully utilize these memory channels. So after this calculation, we then try to fit these kernels, these required kernels to different SLRs. We model it as a multiple knapsack problem because, as you can see, different SLRs actually have different resource capacities because some regions are occupied by some built-in logic like static, like the shell. And also different kernels have different resource utilization. So we can fit them into SLRs by modeling as knapsack problem. So after fitting them into SLRs, then we do the last step, which is interfacing kernels to memory channels. So finally, we can get a synthesizable code which can pass to Xilinx Vertex directly to get a bit stream. So far we have accelerator on hardware. Right? So then we need to explore how we schedule the graph data to fully utilize this accelerator. Because some graphs are too big to fit into the URAMs or BRAMs or FPGA, we actually, as previous study, we adopt graph partitioning. But SunderGP adopts a very simple graph partition method, which is destination vertex cut. Let's see this simple example. Here is the example graph. We have 6 vertices. And let's see the FPGA can only buffer 3 vertices. So in this case, we will partition this graph into 2 partitions with partition 1 buffering vertex 0 to 2 and partition 2 buffering vertex 3 to 5. So for processing, we just scan the edge list and to see and dispatch the edges according to their destination vertex. Let's say in this example, in partition 1, it contains all the vertices whose destination vertex is located in current vertex set. So you can see there is no edge reordering operations or sorting operations, so it's very lightweight, and the complexity is only OE. So after graph partitioning, then we try to schedule these partitions into our hardware. Because we have multiple memory channels. For each channel, we actually have like a kernel group. So since we have multiple kernel groups, in order to fully utilize these kernel groups, we firstly divide a partition into chunks with edges equally divided. This is because for some small graphs, if it only has one partition, if we do not separate it into different chunks, we can only use one kernel group, right? But if we further separate the partition into chunks, we can try to fully utilize the multiple kernel groups. So then we actually developed a regression model to estimate the execution time of each chunk. The purpose is to have a very good scheduling to fully utilize different kernel groups. So then we have a gradient search to find a suboptimal scheduling plan for these chunks. Finally, we schedule this data to kernel groups. So as you can see, after this estimation and scheduling, different kernel groups have similar execution time, such that we can utilize the generated hardware well. Okay, finally, let's talk about the experiments. We actually conduct experiments on two platforms. One has 3 SRs, another has 4 SRs, and we use 7 applications, and we use 19 graph datasets here. So we firstly evaluate the benefits of our memory optimizations. As you can see from this figure, all the optimizations contribute to the performance, and the final performance speed up can be up to 32 times, compared to our baseline. We also evaluate the scalability with increasing the number of SRs and number of memory channels. It's mainly about the memory channels because it's memory bandwidth bounded. Our standard GPU always try to fully utilize the memory bandwidth of the platform. As you can see from this figure, basically it scales pretty well and also pretty close to the theoretical bounds, which is 4 here, because our platforms has 4 memory channels. Finally, we compare with the state-of-the-art implementations. As you can see, compared with the head graph, which is the state-of-the-art, we deliver 2.9 absolute speed up. Note that our implementation is running on real hardware. Theirs is based on simulation, actually. And we consider the real overhead of utilizing multiple memory channels. And compared to GraphOps, which is an HLS-based graph library, we have up to 30 absolute speed up. And compared to our previous work, we have 5.2 absolute speed up. Finally, standard GPU is publicly available. You can find it in GitHub, and also it's featured at Xilinx apps and libraries. Okay, so for conclusion, basically we first saw the challenge of graph processing, especially with the HLS. The problem is data shuffling to solve the runtime data dependency. And then we propose system-level support for graph processing with on FPGAs, with considering both performance and programmability, and also the usability of the system. So for ongoing work, now we are trying to extend FPGA to HBM-enabled platforms, because as we mentioned before, current graph processing on FPGAs is still memory bandwidth bounded, and standard GPU fully utilize the memory bandwidth of 4-channel based hardware platforms. But is that still the case for HBM? Because HBM has up to 32 memory channels, and also the resource is not increased actually. So is still the case we can scale up the number of kernels to fully utilize the memory bandwidth of HBM? So that is the point we want to explore. Yeah, and also if it's not the case, we need to have some design trade-offs to fully utilize to achieve a good performance on HBM-based platforms. Another potential direction can be distributed graph processing, because at this moment graph size is still limited by the onboard memory capacity. Like the FPGA board can only have limited DRAM size. So if we want to process a real big large graph like the graph is larger as human brain, then we actually need a distributed environment to process. Here is the reference about my talk, and finally I want to acknowledge my collaborators and also some grants, and also thanks the Xilinx Adaptive Compute Cluster Program for the hardware donation. Okay, I think that's all about my presentation.
Thank you very much. Yeah, thank you very much. This is really impressive, and I think we're all inspired a lot by your genius ideas, especially the shuffling and also the gas template. And also, we realized that how much work you have done to facilitate user-friendly frameworks. So I think it's really impressive, and we're so inspired by that. I'm pretty sure we're gonna have a couple of questions, so please feel free to ask if you have any questions.
Yeah, I have some questions. Is it? Can you guys hear me?
Yes.
Okay. Yeah. Also, first of all, thank you for presenting. It was really interesting work, especially the memory access and the shuffling. But I had some questions about the graph partitioning specifically. So I understand that you're using the vertex cut. So is this partitioning being done on like some other platform other than the FPGA, or is it like a pre-processed thing on the data set, or is it being done during the runtime of the actual FPGA?
Okay, very good catch. It's a very good question. Actually, this is a pre-processing step, because for some large-scale graphs, they can be reused for multiple times. So we can just like pre-process them and we can store them into memory or disk. Then it's just a once and for all operation.
Okay.
But importantly, we need to keep this pre-processing phase very lightweight. Otherwise, it just diminishing the benefits of acceleration.
Okay, I understand. And then, so when you do the partitioning, do you store like the resulting partitions separately in separate memories, or do you store like index offsets for the partition themselves?
So your question is, we store the partition data and also the index together or separately, right?
Yes.
I think currently we store them together.
Okay. Cool.
It's just like a graph raw data format, just a changed graph, graph raw data. Yeah.
I think I understand.
Because that can enable us process chunk by chunk. Otherwise, the graph is too big. We cannot process totally on chip, right? Now we can process one partition on chip to avoid random memory accesses.
Got it. Thank you so much.
Thank you.
I actually have another question. So could you tell us, for example, so you can support user-defined gather, scatter, apply operations, is that correct?
Yeah, right.
So what kind of user-defined operations is currently supported? For example, are there scalar operations, or you guys can really support complicated operations?
Okay, this is a very good question. I think, yeah. Now, as you can see, we build 7 applications with our system to demonstrate the usability of our system, and we actually also build a demo with our system to predict COVID-19 propagation. So, but so far, I'm not sure there are somebody using our system for other completed scenarios. But basically, I think it can, support the applications that need, edge traverse. Those applications can be accelerated on our system. But if you want to support, like you want to read many variables and you want to buffer many variables in your RAM, then maybe the data paths need to be redesigned, because it's not like CPU. If you want to process one more variable, you just add one more argument. For FPGA, it's different, right? You need to consider all the data paths of that variable, right? So I would say we actually somehow improve the usability of FPGA-based graph processing, but it's still far away from CPU or CPU or GPU-based graph processing, because they are essentially different. One is like hardware, another is software. I think that is the difference, and yeah.
Okay, got it. Thanks. And so, is it true that for all these applications, the apply or the scatter apply is based scalar operations that which have one single value, and we do something to the one single value and then apply?
What do you mean by one single value?
For example.
Okay.
Yeah. Go ahead.
I think. Okay. So basically now we are doing synchronous graph processing. So graph processing basically can be divided into many super steps. So in each super step, we update the vertex property and we do apply. Then in the next super step, we do another propagation according to the previous step updated value.
Yeah.
It's like a BSP execution in terms of from the super step perspective.
Okay, got it. Thanks.
I have a related question on top of that question. So I saw the the COVID SAIR model and in the paper. So
Okay.
Can the vertex property be of any data type? Like, can we define any custom data type for the properties themselves beyond just simple integers or floats? Like, can we customize them as arrays or structs or things like that, or is that not supported at the moment?
Oh, this is a very good question, actually. Yeah, actually, currently our system doesn't support some structure like vertexes. You can actually just change the data type.
Okay.
I mean, if you want to change to data structure, you may need to change other component, not only the APIs. You need to,
okay.
Yeah, change the data flow, how your data structure can pass to current pipeline.
I see. Okay.
Yeah.
Thank you.
Yeah, there
Also,
need some optimizations.
it's also a problem of the on-chip memory.
What?
Yeah, say that again.
Yep.
Oh, I mean, changing the data structure or adding in more complex data structure that also relates to the capacity of the on-chip memory. And you have to do everything that's not exceeding the limit of it.
Yeah, if you have a very, very big intermediate data, that can be also a problem because on-chip RAMs cannot store that. Yeah.
Sure. I'm sorry if I misunderstood this or if you have already explained this, but are you storing the entire graph on chip, or we can swap them out and in?
Not really. For large graphs, we have a graph partitioning. such that we can store the vertex set, only the destination vertex set of one partition into the URAMs actually.
Right. So you're processing the partitions, so partition by partition.
Right. Yeah.
And do you also handle the cross-partition communication?
Because now we are using, our partition method do not, can avoid the, inter cross partitioning communication. Because there are two partitioning methods, edge cut, vertex cut. Our method can, avoid cross partitioning method. Because basically the idea is that we duplicate the vertex. Yeah.
Okay, got it. Thanks.
Yeah, because still I think FPGA is not as flexible as like CPU, GPUs. For CPU, GPUs, there are many solutions. They are exploring, cross partitioning, this kind of stuff. But on hardware, that can be very complex.
Right. Got it. Thanks.
Thank you.
Oh, I have another question as well. So for the whole the gather, apply, scatter with the partitioning, is there like a synchronization block? So do you have to go through and process each partition for the whole graph, and then there's a synchronization block before you go on and do all the partitions again? Is that how the architecture is structured, or can you like analyze the data flow of the partitions themselves and start working on the partition again, but in the second iteration of gather, apply, scatter?
Actually, different super steps. Let's talk about the processing of one super step. For one super step, basically we process all the partitions. After that, we actually need a synchronization because the next super step relies on the updated properties. So we cannot, execute in advance.
Got it. Yeah.
Yeah.
That makes sense.
So it's yeah. Of course, there are some asynchronous execution for graph processing, which is usually done software. Basically, from one vertex, you just keep traversing until it terminated.
Yeah,
but
I've seen.
Go
ahead. Sorry.
Yeah, but in our case, actually, we just traverse one hoop per iteration, per super step, like.
Got it. Yeah, I've seen some literature. They have they can do some dynamic figuring out of the data flow across super steps, but it seems like in some cases it is more hassle to design something like that than keep it simple.
Yeah, that's right.
Yeah.
Got it. This is really cool.
Thank you. Maybe I can stop sharing.
Sure. So from the audience, do we have more questions or any discussions you want to make?
Hello, I'm Yuna Kim and I'm working for Professor Haesung Kim. And I'm very interested in this topic, and I've been working for myself for maybe about a year and a half. So this partitioning work and FPGA, one of the biggest concern for me was graph characteristics. So the graphs, the social graphs, it's really hard to obtain both balanced, well balanced, and also a performance in the perspective of a parallelization. And I can see that it's basically it's a destination cut of a chunk, which is you actually cutting so some all the vertices can possibly have much more number of degrees. Yeah, so I think it's kind of I'm kind of wondering if you did anything extra for for the load balancing.
This is a very good question. Actually, yeah, graph is very hard to balance to fully utilize your whole hardware, right? So, so our aim So SoundGP partitioning, basically we want to achieve lightweight. We want to do things at runtime as much as possible. So for this balancing, actually we do have, because we actually process partition by partition. So we need to, it's like we need to balance sub-partitions of one partition, right? Because we process partition one by one. So there is, it doesn't matter, partitions have different edges. The main point is that when we process one partition, we need to fully utilize all the PEs to process that partition, right? So here comes our idea. We firstly divide a partition into chunks such that we can use different kernel groups from different memory channels to process a subset of this partition in parallel. We just divide our partition into 4 chunks. However, as you mentioned, right? So a simple divide cannot achieve a very good balance, right? Maybe the first partition may takes a lot of execution time. Maybe second is very short, right? So actually here we actually design a regression model to predict its execution time, just that we can schedule different partitions, sub-partitions to corresponding to different kernel groups. Finally, we can achieve a pretty good balance. It's like a graded search. We want the total execution time of one kernel group to be close as possible. So here actually is the balancing technique here.
All right. So then, you actually initially, when you divide the graph, you based on the same number of vertices in the one partition, that not considering any the number of difference in edges. So this actually expected execution time probably is based on the number of edges, right?
Yeah, number of edges. So you can see we actually, according to the edges are equally divided when we process one partition. But still, even the edges are the same. The processing time is not the same because the access has some irregularity. So we still need a mechanism to balancing them to have a global scheduling plan here.
So I'm sorry. Again, just the last question for me. I don't want to take too much time. So from my experience, the number of job, amount of work will be decided by the number of batches and also which algorithm you're running, right? So page rank, active
right.
all the time, everything, and then some traverse algorithm, subset of some edges are active, right? Do you consider that the application benchmark depending on the algorithm, how much work will be, or a kind of yeah.
Yeah, you mean this prediction contain
right? Yes.
We actually consider some, for example, BSP or PageRank. For PageRank, every iteration, every simple step, all the edges you need to traverse, right? But for BSP, it's not the case. We actually consider this difference. Yeah.
Okay.
So far, this is the difference we consider. For others, we haven't considered yet.
It's just one last question. I saw the partition, it's actually vertex partitioning, but you keep the data in COO format. So in that case, actually, could it be just if there's not dynamic graph, it could be CSR or more a compressed format? And do you have any reason for using COO format?
Actually, in our code, we actually process CSR format because it's very easy to translate CSR to COO, right? You just duplicate the source vertices, right?
Yes.
Yes, and also for CSR, the source vertices are already implicitly sorted, right? So here I just want to demonstrate how simple we can do this partition. We just dispatch edges according to their destination vertices to different edge lists.
Okay.
It's just one. Okay.
Yeah, I've been working on this like push-pull algorithm, and I switched it a couple of times for checking my code, and I was wondering like if you have a specific reason for choosing this format. Thank you very much.
Thank you. Thank you.
I'm sorry, I have another question, just one more question about the partitioning. So when you are doing the partitioning, you mentioned that you have a simple, you iterate through the list and you split by destination vertex. So my understanding, and please correct me if it's not correct, that every partition, like you should not have two like of the same destination vertex in two separate partitions, because then you cannot process the partitions separately. Is there sometimes you might have to split the partitions in a way that doesn't align with the size of the memory or on the chip, right? So
Yeah.
is this the case, or is this like a problem, or is there maybe room for efficient graph partitioning so that you can fully utilize all the memories on the chip without having to with some trade-off for some pre-processing complexity, to make the throughput on the device easier, or is it not worth it?
Okay, actually, this is a very, I think it's a very detailed question. So actually, we do this optimization on our implementation, but because for loading and vertex and edges, it's very good. It should be aligned, right, to have a better bandwidth. So yeah, we just do an alignment on software side. Like we're just padding some dummy edges if this partition is not aligned. So this cost is very small because only last chunk, maybe the last few edges, they are not aligned. You just padding some edges, it should be fine. Then you can load in a batch on your hardware side.
I didn't know if it was like a big contributor to performance decrease or resource utilization decrease, but it doesn't sound that major. Maybe if you have graphs with high variability in degree for nodes, but it doesn't sound like it's a super big issue then.
You mean how the graph degree influence this optimization?
Yeah, so for example, if you have in degree that is some nodes very high, some nodes so like if they're all very big, so then you might have to pad a lot in between your partitions because you might be missing a chunk where you cannot fill it with another destination node to fill the rest of the edges.
Well, maybe there is a misunderstanding. We actually do not buffer edges. We only buffer vertex sets. The edge list is stored in the global memory. So actually, you can have a very large edge list for different, and also the size of edge list can be very different for different partitions.
Okay.
Yeah.
Okay.
So we just need to keep the partition vertex set size can be fed into the RAM.
Okay.
Yeah.
Cool. Thank you. Sorry about the questions about the graph partitioning. I'm very curious about the details, so thank you.
All right, cool. I think this is we are very interested in I think the core idea of shuffling is really genius, and also this partition is also very important to the performance. So I think that's why people really care about this too.
Yeah, very good questions.
Okay, do we have more questions from the audience or any discussions? Okay, so if that's all of our questions, I think we can give our speaker a big round of applause and thank you very much for bringing us.
Thank you.
Thank you very much for bringing this interesting topic. And we would like to see you again. If next time you have more follow-up work, and let us know. We will invite you again to discuss.
Yes. Thank you. Okay.
All right. Thank you very much again. And thanks for the audience to join. And thank you all for the insightful discussions and questions. And that is all for our today's meeting. And thank you so much.
Thank you.
Bye bye everyone.
Bye bye.
Bye.
Bye.